Hello everyone, I'm Saliou MBENGUE and today I would like to talk you about this paper focusing on the absorption properties of black carbon at European rural background station. Black carbon or elemental carbon, depending on the detection method, is a minor fraction of atmospheric aerosol emitted during incomplete combustion of fossil fuel and biomass. It is the main aerosolite absorber and considered as the second largest positive radiative forcing contributor after CO2. Beside BC particles, fraction of organic aerosol or brown carbon can contribute to the light absorption, especially at short wavelengths. Therefore, coating of BC by brown carbon can lead to absorption enhancement, leading to larger uncertainties concerning the radiative forcing estimation of BC. The MAC-BC is a fundamental input for climate modeling, defining the relation between atmospheric concentration of BC to its direct radiative forcing. The MAC-BC can be influenced by the physicochemical properties of atmospheric aerosols and the mixing state of BC. Our study focused on long-term measurements of the absorption properties of BC particles at Central European background station in order to characterize the MAC-BC temporal variation at different wavelengths to estimate the light absorption enhancement and the contribution of brown carbon absorption. For this study, we conducted a 5-year campaign at the Czech National Atmospheric Observatory Košetice. The mark of equivalent black carbon was estimated as a ratio between the absorption coefficient from mil2 wavelengths etalometer measurements and the mass concentration of elemental carbon from thermo-optical analyzer, taken as representative of the EBC. As during our campaign, we observed a very good correlation and no significant difference between EC and BC. Additionally, we have parallel measurements of PM10 and PM2.5, combustion trace gases, particle number size distribution, and meteorological parameters as well. The absorption enhancement factor or E-absorption can be estimated as a ratio between the MAC-EBC and its primary fraction or MAC estimated for uncoated BC. This primary MAC can be estimated by removing the coating material on BC particles using some organic solvent or thermodometers or using instruments like the particle soot photometers. For the purpose of this study, we apply a new method developed by Wettal using the minimum R squared in the EC tracer method widely used for the estimation of the secondary organic carbon in atmospheric aerosol. As you can see in this table, by analogy, we investigate the relation between EC and the absorption during etching of particles to determine the primary ratio or the primary MAC corresponding here to the minimum R squared. More data regarding the parameterization of this method can be seen in this paper. For the estimation of the brown carbon attributed absorption, we apply different methods. First, we use the WDA method, which is the wavelength dependence of the absorption Armstrong exponent, define it according to this equation. This method is based on the comparison of our measurements with etalometer to the simulation of delta alpha. As you can see in these figures, all data point above the simulated delta alpha indicate the presence of brown carbon absorption in our samples. On the other hand, We use the Armstrong exponent law to estimate the brown carbon attributed absorption. For this, we use different alpha values for equivalent black carbon. We apply alpha of 1 widely used for soot particles and alpha value calculated from the minimum and the maximum delta alpha estimated during our campaign. Here you can see the months time series of OC and EC, the combustion thrust gases and alpha value observed during our campaign. We have a seasonal variation with high value in winter and low value in summer, opposite to the secondary organic carbon, showing higher value in summer due to the influence of photochemical activity. The alpha value can be used as indication of the source of black carbon. As you can see here, the high value in winter is attributed to the influence of biomass burning. If we look to the absorption coefficient, we found similar trend as for alpha with a more pronounced seasonal variation observed at short wavelengths. This is attributed to the influence of biomass burning emission containing high fraction of organic component. As for the MAC-BC, as you can see here in green, there was no distinct temporal variation at the near infrared wavelengths, but the seasonal variation is improved at short wavelengths due to influence of biomass burning. Here you can see the diurnal variation of the absorption coefficient, showing a more pronounced trend in winter compared to summer. In winter, we have a morning peak attributed to the influence of fossil fuel emission during the morning traffic rush hour, and an evening peak associated to the influence of biomass burning from heating systems. As for the MAC-EBC, there was no clear diurnal variation observed for different seasons. Here you can see the mean MAC-EBC for different wavelengths observed during our campaign for different years. In comparison to previous study at rural background station in Europe, as you can see here, there is a large variability of the values from the literature which can be related to different factors, including the difference in the source and physical chemical properties of atmospheric aerosols, the mixing state and atmospheric aging of BC particles, and also to the detection method used in the different study. But if we focus on our campaign, we can see a decreasing of the MAC-EBC over the 5-year measurements. We perform a temporal trend analysis using Telsen function on the PM10 and PM10 and PM2.5 and the submicron particles. Then we found similar trend as for the MAC-EBC for PM2.5 and the submicron particles, opposite to the PM10. These results suggest that the decreasing of the MAC-EBC during our campaign is likely more connected to a change in the size distribution of fine particles, especially in the submicron fraction. During our campaign, the brown carbon absorption was detected in around 30% of the samples, with a contribution up to 40% of the total absorption measured at short wavelengths. If we look to the seasonal variation, we observe a high absorption coefficient of brown carbon in winter due to the influence of biomass burning. But if we look to the WDA method, we found more fraction of samples with brown carbon absorption in summer, which can be attributed to the increasing formation of secondary organic aerosols during this season. Both sources, you can see here, can contribute to the absorption enhancement, as we'll see in the following slide. Here you can see the monthly mean values of the E absorption and the MAC primary observed during our campaign. We have a seasonal variation of the absorption enhancement varying from 18% in winter up to 60% in summer. This high value of the E absorption in summer can be attributed to the decreasing of the MAC primary and also to the increasing formation of secondary organic aerosols, as you can see here. This result is consistent with the more frequent event with new particle formation in summer, when we have also a high fraction of sample containing brown carbon. These results suggest that in summer we have formation of larger coating and internal mixed BC. During our campaign, the E absorption didn't show a clear wavelength dependence and diurnal variation. For source analysis, we apply different methods. Here you can see the source profile from the potential source contribution function for MAC-EBC and the E absorption at 606 nanometers. We found a comparable source profile for both components, especially in summer, suggesting that the absorption edging of particles is a major driver of the MAC-EBC observed at rural background station. To summarize, we characterize the MAC-EBC as a brown carbon attributed absorption and the absorption enhancement factor during a 5-year campaign. Combining different approaches easily applicable when you have parallel measurements of etalometer and OCEC analyzer. We saw a decreasing of the MAC-BC over the 5-year campaign, likely connected to a change in the size distribution of submicron aerosols. We observed a clear temporal trend of the absorption coefficient at all wavelengths, while for MAC-EBC, seasonal variation appear only at shorter wavelengths due to the influence of biomass burning. During our campaign, brown carbon was observed to contribute significantly to the total absorption at shorter wavelengths. In summer, we have high E absorption attributed to the larger coating of BC particles. The mixing state of BC particles is considered as a major driver of the MAC-EBC observed at rural background station. Consequently, further investigation dealing with the composition of the coating material on BC particles are needed for better characterization and understanding the uncertainties related to the estimate of BC radiative forcing. Thank you for your attention. You can see my email address for your questions and comments.